At the outer frontier of our solar system, Voyager 1 encountered something that sounds almost impossible: an enormous region of extremely hot plasma separating the Sun's domain from interstellar space. This was not a solid barrier, and there was nothing resembling a physical wall waiting in space. Instead, Voyager entered a boundary region where solar particles, magnetic fields, and material from the space between stars interact in ways that scientists are still working to understand. The temperatures measured around this region can reach tens of thousands of Kelvin. That sounds terrifyingly hot, far hotter than the visible surface of the Sun, but there is an important detail that changes the entire picture. The plasma is incredibly thin. There are so few particles that the spacecraft does not absorb anything close to the amount of heat you might imagine from the temperature alone. Voyager 1 crossed this extraordinary boundary in 2012 and continued operating afterward, sending measurements back to Earth from billions of kilometers away. Its signals take many hours to reach us, and every tiny piece of information is precious. To understand what Voyager discovered, we first have to understand what the edge of the solar system actually is. Most people imagine the solar system as a collection of planets surrounded by empty space, with Pluto somehow marking the end. But the Sun's physical influence extends vastly farther than the planets. The Sun constantly releases a stream of electrically charged particles called the solar wind. These particles race outward from the Sun, carrying energy and the Sun's magnetic field with them. Together, the solar wind and the solar magnetic field create an enormous bubble around the solar system called the heliosphere. This bubble is not perfectly shaped, and it is not a rigid structure. It changes over time because the solar wind itself changes with the Sun's activity. Far beyond the planets, the outward-moving solar wind eventually encounters material belonging to the interstellar environment. The pressure from the solar wind competes with the pressure of the surrounding interstellar medium. Eventually, the solar wind can no longer continue expanding freely. The transition happens through several different regions. First comes the termination shock. This is the region where the outward-flowing solar wind slows dramatically after encountering increasing resistance from the surrounding interstellar environment. Voyager 1 crossed this region in 2004 at roughly 94 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun, so Voyager was already enormously far from home when it encountered the shock. The spacecraft's instruments detected major changes in the surrounding particles as the solar wind transitioned into a slower and more turbulent state. Beyond the termination shock is the heliosheath. This region sits between the termination shock and the heliopause. Here, the solar wind has already slowed down, become compressed, and developed strong turbulence. Voyager's journey through this region lasted years. Instead of finding a simple, peaceful transition zone, scientists observed shock waves, changing magnetic conditions, and variations in the plasma environment. Voyager 2, which carried a functioning plasma instrument capable of making direct plasma measurements, provided especially valuable information about the conditions in this region. The data showed that the outer solar system was much more complicated than the simplest theoretical models had suggested. Eventually, Voyager 1 approached the heliopause, the boundary separating the heliosphere from the surrounding interstellar medium. On August 25, 2012, Voyager 1 crossed this boundary at approximately 121.7 astronomical units from the Sun. The evidence came from several measurements. The population of low-energy particles associated with the solar environment dropped dramatically. At the same time, high-energy galactic cosmic rays increased. The plasma density also changed significantly, and the spacecraft detected changes in the magnetic environment. Together, these observations showed that Voyager had entered interstellar space. And this is where the famous "wall of fire" description comes from. Around the heliopause, measurements indicated plasma temperatures reaching tens of thousands of Kelvin. At first glance, that sounds like a spacecraft should have been instantly destroyed. But temperature and heat are not the same thing. Temperature describes the average energy of individual particles. Heat transfer depends on how much material is actually present and how effectively that material can transfer energy. The plasma surrounding Voyager is extraordinarily sparse. So even though individual particles can have extremely high energies, there are so few of them that the total amount of energy transferred to the spacecraft is tiny. Imagine the difference between standing next to a roaring furnace and encountering a handful of extremely energetic particles separated by enormous distances. The particles can individually be moving incredibly fast without carrying enough collective energy to burn the spacecraft. That is why Voyager could pass through this extremely hot plasma without being destroyed. The wall of fire was therefore not a literal wall of burning material. It was an extremely unusual plasma environment located at the boundary between the heliosphere and interstellar space. So what makes this region so hot? One important factor is compression. As the solar wind encounters the outer boundary of the heliosphere, its particles become compressed. Compression can convert part of the particle's kinetic energy into thermal energy, increasing the temperature. Magnetic fields add another layer of complexity. The heliopause is a place where the sun's magnetic influence interacts with the magnetic field of interstellar space. Magnetic fields embedded in plasma can become distorted, compressed, and reconfigured. Processes such as magnetic reconnection can release stored magnetic energy and accelerate particles. The result is an environment far more dynamic than a simple line separating one region of space from another. Voyager also discovered something surprising about the magnetic field just beyond the heliopause. The magnetic field measured in the local interstellar environment showed a relationship with the magnetic field inside the heliosphere that scientists had not expected to be so strong. Voyager 2's crossing in 2018 provided another set of measurements that helped scientists understand this behavior. These observations suggest that the region immediately surrounding our solar system is not simply untouched interstellar space. The Sun influences its surroundings. Its magnetic field and solar wind interact with the surrounding interstellar medium, shaping the environment beyond the heliopause. The boundary itself is also not fixed. Voyager 1 and Voyager 2 crossed the heliopause at different distances from the Sun. Voyager 1 crossed at about 121.7 astronomical units, while Voyager 2 crossed at roughly 119 astronomical units. That difference is consistent with the idea that the heliopause changes position as solar activity rises and falls. When the Sun becomes more active, the solar wind can push the heliopause farther outward. When solar activity decreases, the surrounding interstellar pressure can push it inward. So rather than being a permanent wall sitting at one exact distance, the heliopause behaves more like a dynamic interface responding to forces from both the Sun and the galaxy. The region around the boundary also contains compressed plasma. Material can accumulate on both sides of the interface, showing that the heliosphere is being shaped simultaneously from within by the solar wind and from outside by the interstellar environment. This makes the heliopause less like a simple border and more like an enormous, constantly changing interaction zone. But perhaps the most important thing Voyager revealed was not the temperature. It was what happens to radiation when the spacecraft leaves the heliosphere. Inside the heliosphere, the Sun provides a degree of protection from galactic cosmic rays. These are extremely energetic particles produced by violent events throughout the galaxy, including supernova explosions and other powerful astrophysical processes. They travel through interstellar space at enormous energies and can be hazardous to living organisms. The solar wind and the Sun's magnetic field help deflect some of these particles away from the inner solar system. When Voyager crossed the Heliopause, its instruments detected a dramatic increase in high-energy galactic cosmic rays. That provided direct evidence that the heliosphere acts as a measurable radiation shield. The boundary was therefore not merely an interesting feature of space. It marked a significant change in the radiation environment surrounding the spacecraft. Voyager's ability to make these measurements is remarkable in itself. The spacecraft was launched in 1977, long before smartphones, modern personal computers, or today's communication technology existed. Its electrical power comes from radioisotope thermoelectric generators that convert heat produced by radioactive decay into electricity. Those generators have been losing power gradually for decades. Engineers have therefore had to make difficult decisions about which instruments can remain active. As the available power decreases, some scientific instruments have been turned off so that the remaining systems can continue operating for as long as possible. The instruments that remain are especially valuable because they continue measuring the magnetic and plasma environment of interstellar space. Voyager is essentially conducting an experiment in a region of space no other currently operating spacecraft can directly sample in the same way. And there is another extraordinary part of the story: getting the information home. Voyager 1 is so far away that its radio signal becomes incredibly weak by the time it reaches Earth. The spacecraft's transmitter operates at only a few tens of watts.